So, another look at the future of mankind, and this is the second phase of space colonization. The first phase is just colonizing our own solar system, and that is going to give us it'll give us resources for hundreds of thousands of trillions of humans. But of course, once you've done that, and then you say, what next? You realize that, it's again like you're in Zanzibar and you're looking at the African mainland. And you've colonized our solar system, and then you're looking around and you're seeing the rest of the galaxy, which are like many more different solar systems. And you kind of ask yourself, is this it? Are we just going to stop at our own solar system? Why not go and also colonize Alpha Centauri, which is essentially a system of 3 stars. Lots of mass there, which can be converted to space habitations. And the question is, it's very far. It's about over 4 light years away. And then the question arises, would it be possible, given our present knowledge of physics and based on our present knowledge of the laws of physics, is it possible to actually build an interstellar colonizing vessel? Okay. So I'm going to describe the design of a vessel, and it's important to understand that these are all consistent with what we know of physics now. There is nothing like, that someday we're going to do like wormholes and we're going to travel faster than light, blah, blah, blah. No, none of that. Okay. This is proper science. You don't say those things if you're a proper scientist. Love to be proven wrong, but I don't think it's going to happen. Okay, so what is the design for this colonizing vessel? Well, essentially it is based on the design for a space habitation with an engine added to it. Okay, and there are some design goals for it. The first goal is that the population of a ICV flotilla, so there'll actually be 10 of them. Okay, so there will be 10 of them in a flotilla. It won't be just one spaceship by itself. That's like kind of risky. You'll get bored. You want a variety of landscapes. Some one ICV will be like a tropical island inside of it. The other one will be like a alpine mountain ranges, and another one could be just a city, a major city. So just a variety. That's one thing. The second thing, why you would rather have a flotilla of 10 ICVs rather than one ICV is that it reduces the risk. If there's some damage happens to one ICV, then the remaining ICVs can help repair it, or they can evacuate the inhabitants. So this design for the flotilla is based on 10 ICVs in the flotilla. And the total population of the flotilla will be 12,500. And so that's a design goal. And the nuclear fuel needed for the flotilla should not be more than 1.5 times the average global production of uranium-238 from 2013 to 2022. So I just have to, when you're designing these things, you have to, a constraint is obviously fuel, and you're going to have a design with nuclear fuel, and you just can't say that, oh, I'm going to use this fantastic amount of fuel, so let's just keep it within 1.5 times the global production of uranium-238. Uranium-238 is actually quite a commonly occurring metal, and in fact thorium is even more common. So let's look at, so it's essentially a space habitation with the engine attached. And then, now what about this engine? So the engine, ejects something, law of conservation of linear momentum. You got to throw out something at a very high speed to get some action and reaction force to be able to get to a high speed. So let's say chemical rockets and all just won't work, okay, because the speed at which they eject mass is just too low. So what we are going to look at is we are going to look at electromagnetic railguns as the for the engine, for the rocket, and it is going to first there's a calculation of how much electromagnetic railguns actually, what acceleration they achieve, and there is one experimental electromagnetic railguns designed by BAE Systems, unfortunately a defense contractor, which of course I'm no fan of defense contractors, but this was the data I could find, so here they are. And it's 114,920 meters per second squared. That seems to be around what they were able to achieve, the acceleration, or it's about 12,000 G. That may seem very high, but actually it's apparently like these railguns can achieve accelerations of 100,000 to 200,000 Gs. Okay, so then the railgun for this ICV is going to be 20 kilometers long. It may seem a very large rocket, but 20 kilometers is nothing. Think of just a few hundred years ago, what did we have? We had canoes, and now we have cruise ships. Just compare the size of a canoe and a cruise ship, and you can sort of understand why we should not, based on our current experiences, believe that, oh, this is what is feasible and this is not. Okay. So just a 20 kilometer railgun has an acceleration of 114,000 meters per second square. So the velocity of the eject is 67.8 kilometers per second. And that is very much larger than what you would get from a chemical rocket. So that's the point of having an electromagnetic railgun. Okay, the mass that you shoot out can be at a much higher velocity. And then we apply the Tsiolkovsky rocket equation, which basically tells you if you start with a certain mass and you eject a certain percentage, a certain fraction of it, what is the velocity, the change in velocity of the remaining mass, the remaining rocket, which has ejected that mass. And that turns out to be, if you're ejecting the mass at a speed of 67.8, then the remaining rocket would have a speed of 15.13, assuming that 20% of the mass was ejected. And why not eject more mass and get an even higher velocity? Well, you also want to have the rocket to provide habitation. So it needs agriculture, it needs parks, it needs bike trails, it needs all kinds of things for luxury. So we assume that it's going to eject 20% of the mass. And this is at the beginning of the journey. Okay, then I actually, in an appendix, I also work out the numbers for gravity assist. And the gravity assist numbers I work out are from a maneuver in which you reverse the direction of orbit of the ICV and you shoot it, and you kind of get on gravity assist from Venus. And because the ICV and Venus are traveling in opposite directions, you get a very significant gravity assist. And the speed that you get, of course, there's after the gravity assist from Venus, it has a certain speed. But then by the time it exits the solar system, the speed will fall because it has to pay a certain amount of energy to overcome the gravitational force of the sun. So it's going to lose some amount of kinetic energy, which is going to be converted to potential energy. And then what we have is that the velocity, departure velocity, is going to be 63.54. And after that, you will fire the engine and you'll get an additional 15.13 kilometers per second of velocity. So your total velocity in space after you exit the solar system and after you fire the rocket engine should be about 78.67. And then you're headed towards Alpha Centauri, right? And Alpha Centauri is actually moving towards us. So the velocity at which it will approach Alpha Centauri will be about 89.60. And so there was a certain amount of fraction of mass that you had to eject to get your acceleration. And next, there'll be a certain amount of mass you'll have to eject again to get the deceleration. You have to slow down when you approach. You just can't shoot past Alpha Centauri. You have to slow down. So there are some calculations. This is the orbital velocity around Rigel Centaurus. I think this is maybe a Europeanization of an Arabic name, an Arabic astronomer who first identified or did something. Anyway, so Rigel Centaurus, if that's where the ICV is headed and that's the destination, its velocity will be 31.24 in orbit around Regal Centaurus. So your velocity of 89.6 kilometers per hour has to be reduced to 31.24 kilometers per hour. And there is another thing that you must remember is that when you're approaching Regal Centaurus, you'll be accelerating because you're losing potential energy when you're approaching the star and it's getting converted to kinetic energy. Okay, now assume that you get a 20, and then gravity assist can also be used for braking. So assume that you get a 25 kilometers per second braking from any planet in that solar system. I don't know, maybe you could even try braking using the star. But anyway, just assume that it's 25 kilometers per hour. So the velocity after you fire the rocket engine to decelerate, that would be, and when you are in Regal Centaurus orbit, so you want the speed to be 56.24 kilometers per second. And this would be also, you have to account for the fact that this is a higher velocity than the end of the rocket deceleration because of the kinetic energy which has been added. So this is the loss in potential energy which will appear as kinetic energy. So you need to get the velocity of the ICV all the way down to 34.8 kilometers per second when you approach the Regal Centaurus system, the star with its surrounding planets and all that. So your velocity was 89.6. That was the relative velocity with the star, and you need to get it down to 34. So the amount of deceleration is 54.8 kilometers per second. And then again you use the rocket equation, and what you get is that the fraction of mass that you must reject is 55.43, or because you rejected 20% earlier, so of the initial mass, that 55.43% is 44.35% of the initial mass, or the total mass ejected during acceleration and deceleration is 64.35%. So it will, at the end of its journey, retain 35.65% of its starting mass. The details are there in the book. Just get the book. So you start out with the thing weighing 142 billion kilograms, and at the end of its journey, it is going to have a mass of 50.62 kilograms, and each ICV had a population of 1,250 humans. So at the end of the journey, the amount of mass which each ICV will have will be 40.49 million kilograms per human. And one of the design goals we had set was that it should be more than 36.92 million kilograms per human. Now, is that sufficient mass really to have a closed ecosystem which can support life? It is a pretty large amount of mass. You just think about, let's say, a cruise ship, which of course doesn't produce its own food, but it does like accommodate people, and it does have facilities for entertainment. So a cruise ship, the average mass per capita is only 11,370 compared to 40.49 million for the ICV, and so that the ICV is going to have a per capita mass which is greater by a factor of 3,560. So that kind of gives you an idea. I mean, these are conservative estimates. Of course, ICV has to produce food. Okay. Now, the time it will take to get to Alpha Centauri is 14,000 years. And you're going to say, no way, I'm not going to spend 14,000 years in a spaceship. And then the point is that, the solar system is going to be around for, let's say, 1 billion years, right? So what are you going to do? I mean, what's humanity going to do? Are they just going to sit on their hands and wait for the sun to blow up in 1 billion years? Or spend a very small fraction of that billion years and get to Alpha Centauri, and from that get to the next solar system, and then the next solar system, and then colonize the whole galaxy? Yeah, 14,000 years seems like a long time. But we have so much time. We have 1 billion years at least, right? Now we're just going to sit and wait for the sun to become a red giant or something and fry us? No, we won't. We are going to move on to the next solar system. And the life on these ICVs is going to be luxurious, right? Because the design was always, starting with the space habitation, the design was always luxury. That's why people are going to do it. They'll be achieving something great. Making humanity a multi-solar system species. Okay, so given these numbers, we have to now, we'll now make an estimate of energy requirements. So you have energy requirements for agriculture. Then you have energy requirements for the rocket engine. And so you have a total energy requirement. It's all very plausible. There's nothing fantastical going on. For example, when I say energy requirements, I'm just assuming that the energy conversion is only going to be 75%. So the energy requirement will therefore increase from 3.948 to 5.265. Any scientific issue which I could think of, and I believe I've thought of all of them, or at least most of them, I have not neglected just for the sake of, let's kind of have a design to. So everything I have tried to make it accurate. And here, for example, I've said, okay, currently we have turbines with an efficiency of 64%. And so let's say this is the second phase of space colonization, and it's going to be many hundred years or even 1,000 years before we actually embark on this journey. And Okay, so obviously, chemical energy is obviously out. It just doesn't have enough energy density to think. And then you have there are two things. One is fusion, and these are the different possible fusion reactions. Or so the energy available, like from one of them, let's say two atoms of deuterium and 1 kg, so from the energy available from 1 kg of deuterium to be 3.015 into 10 to the power 14. Now fusion reaction is actually, fusion energy is actually very popular with, it's very popular with people who think of the future or think of powering a rocket. And the point being that if you compare the fusion energy, and that density is 3.015 into 10 power 14 joules per kg, and then you compare that to uranium-235, which is 8.354 into 10 power 13. So deuterium is about, the energy in deuterium is about 4 times as much. However, I do certainly hope that we get to a point where we can have fusion energy, but like I said, this is about not making anything that we already don't know is possible. Fusion energy is very difficult. You think of, even if you have the energy towards the center of the sun, has fantastically high temperatures and pressures, even there, the amount of deuterium, the amount of hydrogen which fuses and produces energy is really a very small fraction. So I certainly hope someday we will get to fusion energy, but just saying that we are going to get there is not, one can't make that claim that will actually happen. So I'm just going to stay with fission energy. That's the bottom line. Even though it's only 1/4 of the energy density, I'm just going to consider fusion energy. And then given our energy requirement, the mass of the uranium to fuel it would be 7.877 million kilograms. And then the mass of, as a percentage of the initial mass of the ICV, it is only going to be 0.0055%. Okay? So it's only fission energy is fine. Uranium is fine. It's not good, you aren't going to need a whole amount of uranium to get to Alpha Centauri. Later in the book, I actually talk about getting to the Andromeda galaxy, and there you do actually need a huge amount of uranium. But right now, that's phase 3, and I'm not talking about phase 3. I'm just talking about phase 2 right now. Phase 2 is getting to Alpha Centauri. Okay? Getting to Alpha Centauri in a spaceship which has enough mass to set up new space habitations in the Alpha Centauri solar systems. And one advantage always of using fission rather than fusion is that the result from the fissioning of uranium or plutonium, you produce metals. And metals are good because they can be used as rocket ejects. You can just shoot them out. And that becomes it's not so important, that's not really important consideration, because it's only 0.005% of the rocket mass. So it's not that important for ICV. However, when you're going to the next galaxy, that becomes an important issue. Now, there is something about, interstellar space is not really completely vacuum. There are small amounts of dust particles, and it's called cosmic dust. And there's been some discussion about it, and it said that for a large spaceship traveling at 45,000 kilometers per second, and ours is much, much slower, it needs a dust guard of 50,000 kgs. And so we're just going to travel at 1/500th that speed, and the kinetic energy of the particle striking it will therefore be 1/250,000. Okay, and even like 50,000 kg of a dust guard is just really a small amount. Another researchers have said that if the speed is less than 1% of light speed, then you won't even need that, because the kinetic energy of the particles are very low. So 1% of light speed is 3,000 kilometers per second, and the velocity of the ICV will only be about 78.67 kilometers per second. So this is not going to be an issue. Okay. Then, and finally, there are two more things I want to say. The second last thing I want to talk about is engine power. You may think that this is like a 142 billion kilogram ICV, and you're accelerating it to this very high speed, and you think that it is actually going to need a lot of power. It has to have a very powerful engine, and the answer is no. It only needs an engine which has about 1/10 the power of a Tesla 3. How is that possible? You have to read the book. Yeah. Okay. So these ICVs, the flotilla, there'll be a train of ICV flotillas. So you shoot one ICV flotilla 1,000 years from now, then you shoot another one 2,000 years from now, another one 3,000 years from now. That will also help with communication. So you'll have a whole train of ICV flotillas headed towards Alpha Centauri. And the ICVs in a flotilla will likely be all docked onto a gigantic ring. This will make transport possible between the different ICVs without the use of any rocket eject, and which is important. You don't really want to shoot off Mars. Mars is really the scarce commodity. Now, this is similar to space habitations when you build them in our solar system around the sun. They will also be docked onto gigantic rings so that people can travel from one space habitation to another on a train in the ring, rather than using rockets to travel from one space habitation to another. Because we are looking at, these space habitations are supposed to be, provide us a home for 1 billion or more years. So you just can't keep shooting out rocket eject mass to get from one habitation to another. You're just going to run out of mass very quickly. Quickly in the sense that in a few million years maybe, but you want to be there for billions of years, right? So the space habitations are going to be docked to a ring. Similarly, the ICVs will be docked on a ring, which will enable travel between the ICVs without any mass ejected. Okay, there are many more details about this ICVs. You should, like, they're in the book. Read it.